My name is Sal Salas, and this is my lightning talk on topographic survey of a braided river system using terrestrial laser scanning. Now, this river system is the River Feshie in Scotland, and the purpose of the study was to create a high quality digital elevation model of the river channel topography. The DEM would be used for hydrodynamic simulations to study erosion and the sediment displacement. And they also were looking for a platform, a survey platform that would allow for multi-temporal surveys to study any kind of topographical morphing caused by river flow or extreme natural events. So the method, like I said, was terrestrial laser scanning, or TLS. This is an active remote sensing platform that it produces its own energy in the form of a laser that gets reflected back to the sensor to record the measurements. So the scanner itself will rotate in 360 degrees along its horizontal axis. At the same time, the laser and sensor on the vertical axis will be spinning at a very high rate of speed, collecting millions of points per second. As the laser is reflected off the object and bounced back to the sensor, a distance, horizontal, and vertical angle will be recorded, creating millions of points worth of data that is saved into a point cloud. So the benefits of TLS is that it's similar to airborne LiDAR in that it provides an immense amount of survey data, survey grade observations, and it creates these dense point cloud data sets that are extremely accurate and precise. Because of the immense amount of data and the resolution that it's collected at, that it can create multi-scale perspectives to fit project needs and construct multiple DEMs at different resolutions and grid sizes. And the data, although large, can be easily processed and exported to useful platforms such as GIS and CAD platforms. And of course, because the way the data is acquired, it's such a massive rate, it oftentimes, depending on the project, will outperform traditional survey methods such as GPS and total station, and especially if it is deployed on a mobile platform. So the method and approach used, on the left you see it's about a 1 kilometer stretch of the River Feshie, and the red dots are the scanner locations and the yellow triangles are the control targets set up. Because the laser scanning is limited to line of sight, unlike LiDAR, the laser that is emitted does not penetrate objects, so things like vegetation, any kind of visual obstructions, will affect what is actually collected in the field. Therefore, multiple overlapping setups are needed in order to get all the data that's required for, high quality DEM. Each one of these setups is going to have its own point cloud, more than likely millions of points of data, and these point clouds will be registered and stitched together using this network of control targets that will be set up and overlapped with each scan. So some comparisons between a traditional GPS survey that was performed as well as the laser scanning. The differences in the project time: the GPS took 14 days versus a few days with the laser scanning. And the amount of observations is roughly 34,000 versus 330 million on the laser scanning. And the point density was an abysmal 0.17 points per meter squared versus up to 400,000 points per meter squared with the scanning. And there was a mean 3D error of about 40 millimeters versus 70 millimeters. So the result, after all the point clouds are stitched together, is an extremely high quality model of the riverbed and the topography. And you can see on the left that it can be used at multiple scales, at the granular scale, the bedrock scale, or the different braided channels, depending on what the project and study needs call for. The study also wanted to do some quality assessment on the actual elevation models produced. So on the left, you can see a grid, a table showing the grid size as it was degraded from zero point 0.1 meter all the way down to 10 meters, and the difference in elevations on the heights and the number of observations that were actually used for the different grid sizes. And as a visual on the right, you can see in figure B, you have the cross section of A and B and C and D, which are shown down here. And you can see as the grid sizes are degraded, you can see how it severely starts to affect the quality of the DAM and the amount of detail that is kept. And this will severely affect the simulation, the hydrodynamic simulations that they wanted to perform. An added bonus to the scanning was that they were able to do some post-processing and distinguish what was vegetation, what was granular sand, what was cobblestone, whatever made up the bedrock of the river. And some conclusions, they found that it was extremely efficient in the post-processing of these large data sets, as they were able to export into whatever platform they needed. And it gave them the flexibility of decimating these point clouds into whatever resolution they needed for multiple studies. And that they found out that the quality of the hydrodynamic modeling and analysis was severely impacted based on the grid size it was degraded to. And of course, future surveys were combined onto mobile scanning platforms, which greatly increased the project scale. As you can see here, there's another braided river system in New Zealand that used a mobile TLS survey. This one's about 3 times as long as the previous and still kept the amount of resolution and high quality with about 6 billion points.